we'll be discussing the remaining IoT connectivity technologies. Before watching this video, I would suggest you to go through the past two videos because we have covered nearly 10 to 12 IoT connectivity technologies. So here we'll be covering the rest of technologies. So first one we have is Sigfox here. So Sigfox is a low power wide area network, that is LPWAN protocol, designed for applications requiring minimal power and infrequent or small bursts of data transmission. So here the main focus goes into the minimal power consumption and infrequent and small bursts of data transmission. So it is mostly used in sectors like building automation, smart metering, agriculture, and security. So the technology leverages ultra narrowband UNB transmission from improved resilience and efficiency. So speaking of the key features of Sigfox, first one we have is ultra narrowband technology. That is, it utilizes 192 kilohertz bandwidth for communication. So here each message will occupy 100 hertz of spectrum, thereby reducing the noise and interference effects. Then it is very robust against jamming and high noise environments. That is, speaking of this ultra narrowband technology, it is very efficient or preferred even in noisy environments. Then speaking of the frequency bands, in Europe it is in 850 to 900 megahertz, and in rest of the world it is 902 to 928 megahertz. Speaking of the data rate, it achieves transmission rates between 100 to 60 bits per second. And speaking of the message encoding, so it employs binary phase shift keying for encoding data. So optimized, the data rate is very optimized for low throughput IoT applications, making it again beneficial. Then speaking of the next point which we have is security. So in terms of security, it implements AES algorithm for authentication and integrity. It protects against any sort of relay attacks which are happening. And not just that, even the payload, so payloads of 0 to 12 bytes are supported here. So this is very sufficient for the sensor data, GPS coordinates, and so on. Next we have communication. So it makes use of asynchronous and bidirectional communication with higher upper link budget than the downlink. So these were the key features of Sigfox. Let's now look into the figures. So the first figure we have is Sigfox communication architecture. So the first one we have is endpoints here. So if you see, endpoints are any IoT devices, it could be sensors that will generate the data and transmit the data further to the base stations. So here it is low complexity and low power consumption. These are the features of endpoints. Speaking of the base stations will monitor the entire spectrum for UNB transmission. So it utilizes cooperative reception to receive the signals from multiple devices. Speaking of cloud backend, so cloud backend will process the data and it will store the data from the base stations. Yeah. Speaking of random access principle here, it devices transmit messages at random frequencies, right? So there is no proper scheduling or defined method. So this randomness will enhance the reliability and reduce collisions. So we have seen here we make use of Sigfox protocol. Here also the same protocol is used, and in order to transmit the data, we make use of TCP/IP protocol. So this was about the communication architecture. Next, let's look into Sigfox protocol versus ISO OSI stack comparison. So firstly, looking at the application layer, it is similar to OSI, handles application specific logic. Speaking of the frame layer here, so it combines presentation layer, session layer, and transport layer. Okay, so coming to medium access layer, access control, sorry, MAC. So it manages access to ultra narrowband spectrum, which is similar to OSI data link layer. Then speaking of physical layer, it is the same. It handles encoding and transmission through UNB medium. Speaking of the applications, in applications, first one we have is smart meters. So smart meters like gas, electricity, water meters can be, this technology could be used there. Then agriculture, we have soil moisture and livestock tracking and all of that. Then security is alarm systems or building automation and all of that. Environment monitoring could be pollution sensors, weather stations, and so on. Asset tracking is again, as we have discussed, logistics, supply chain management, monitoring, and so on. Speaking of the advantages and disadvantages here, so let me write it down. In the advantages, first one we have is low power consumption, and second one we have is wider area coverage. Third one is it is resilience, that is very effective in noisy environments and resistant to interference. And scalability is it is ideal for dense IoT deployments. Speaking of the disadvantages now, so first one we have is low data rates. So it is not suitable for applications which have high throughput. Then we have asynchronous communication happening here. So it can be limited to only downlink capabilities, not used everywhere. Then we have payload restrictions, only 10 to 12 bytes as we have discussed earlier. And not just that, we have limited mobility also. So it is only suitable for static deployments. That is, it can be only used in sensors and so on. So these are the drawbacks of Sigfox. Ultimately, to sum up, Sigfox is very effective, low power consumption, where battery guarantee is there and reliable communication is there. But then it is not suitable for high speed or large payload use cases. So this was all about Sigfox. Let's move further. We have long range now. So long range is a patented wireless technology developed by Cycleo. So it is or a Semtech subsidiary. So it is widely used for low power, low range communication in IoT and machine to machine applications. So long range operates in sub gigahertz frequency bands, that is 169 megahertz, 433 megahertz, 868 megahertz, and 915 megahertz, enabling communication over distances ranging from 15 to 20 kilometers with low data rates, that is 27 to 50 kilobits per second. So the main features here are spread spectrum modulation with chirp coding, allowing higher receiver sensibility and robust communication. Next, moving on, we'll discuss the features here. So the first one being the frequency bands which we have discussed. It is ISM bands only they are using here. Then communication range is again 15 to 20 kilometers. We have discussed this, and the data rates here are 27 to 50 kilobits per hour. And next we have is the battery life. Battery life, it is optimized for long battery life. Then it supports multiple devices, millions of devices, that is network scalability. Then speaking of mobility, it is ideal for asset tracking and management due to excellent support for mobile devices. Speaking of the other features, so security features. First one is the network layer. So network layer, it secures communication to network level. Network key is used here. Then we have application layer, application key, which provides end-to-end security at application level, and device-specific key, which is very unique for each and every device, and it will help us for identifying the devices uniquely. Next, let's look into this figure. So a typical long range so a typical long range deployment and communication architecture is here. First one we have is the endpoints here. Endpoints can be sensors, actuators which collect the data and pass it further. Then we have the protocol or the technology here, that is long range or long range wireless area network. Then we have gateway here. Gateway act as intermediate. It will forward the messages between end nodes and the network server here. So gateways are connected to network server via IP based, or it could be wired or wireless connections. Here it is 3G or Ethernet. Then we have network server here. Network server handles tasks like message scheduling, data rate optimization, redundancy elimination, and all of that. It ensures that reliability is maintained. And security, again, security is also a key aspect. Then we have application layer. So this hosts the end user application. It will process and visually uh, produce the output to user. Yeah, so this was all about the deployment and communication architecture. I have written down all the key points to remember or write an exam. So next, moving on to the protocol stack here. So the first one we have is application layer. Application layer will define whatever the logic is there, application logic, and protocols which is very specific to the services which are being accessed. Then we have MAC layer. So it will handle medium access control, so scheduling, acknowledgements, all those things. Then we have PHY. So physical layer will implement the chirp, spread, spectrum modulation, and which will make sure that there is robust transmission happening. Then we have RF layer. RF layer is responsible for actual radio frequency transmission and receiving the signals back. So here I have written down. So if we compare the long range and long range wireless area network, so we can say that long range refers to physical layer technology, whereas long range wireless network is a network protocol which is built upon long range. So this will enable end-to-end communication between the IoT devices. Speaking of the characteristics, long range networks are mostly in star topology. They have redundant message reception and again chirp coding gain, which we have discussed here. Now let's look into the applications. First one is the smart cities. So street lights, waste management and all of that. Then agriculture, soil moisture sensing, irrigation control and all of that. Utilities, smart meter for electricity, water, gas, logistics, that is supply chain monitoring, asset tracking and all of that. So speaking of the advantages, long range, yes. Then low power, that is proper battery life is there. Scalable, it supports many devices, and secure. We have robust encryption and decryption algorithms that will make sure that data is protected. Next, along with this, let me also write down the disadvantages. So the first one is low data rates. So in case where high throughput is required, such things in such applications we cannot make use of these technologies. Then again, latency is again one more point. So longer transmission times compared to the normal cellular technologies. Then we have interference. So wide spectrum usage compared to ultra narrow band, that is in Sigfox case we have discussed, right? So this was about long range. So moving on further, we have narrowband IoT now. So narrowband IoT is a cellular based IoT technology developed by third gen partnership project 3GPP, aiming to deliver highly reliable and energy efficient solution for IoT applications. So it can operate with existing cellular networks. That is one of the major advantages. It is typically over 2G, 3G, 4G and provides a low power wide area network solution. So narrowband IoT is particularly suited for applications that require small amount of data transmission with longer battery life. Speaking of the key features, first one we have is a better spectrum efficiency and system capability than other technologies. So it ensures stable communication even in dense area networks. It supports battery life is being spoken here. Up to 10 years of battery life is being provided here. Then it uses OFDM, orthogonal frequency division multiplexing. So this, yeah, to improve the system capability and spectrum efficiency. It supports confidentiality, authentication, and integrity features, ensuring secure communication. Then it is well suited for static IoT applications, environmental sensors. It does not support any mobility. No mobility support is provided here. Or we can say it is not suitable for applications which involve moving devices or high speed data transfer. So this allocation of narrowband IoT within the LTE spectrum. So first one we have is GSM band. GSM band, narrowband IoT utilizes GSM band. This is usually around 200 kilohertz, and this is used for communication purpose. It will allow us to make use of existing cellular infrastructure and avoid requiring any dedicated spectrum. Then speaking of guard bands are unused parts of LTE spectrum that are typically left between the channels to avoid any interference. So narrowband IoT can utilize these guard bands, which ensures minimal interference with the existing LTE systems. Then we have the LTE spectrum here. So narrowband IoT operates in a narrow 200 kilohertz channel, which is very smaller than the other standard LTE communication channels, right? So this narrowband or this narrow channel is the key reason why NB-IoT can supply many more devices with lower energy consumptions. So I have written down all the points here. Next, moving on to the figure 7.24, the NB-IoT protocol stack with respect to its entities. So first one we have is UE. UE is user equipment. User equipment could be the sensors, meters that are connected to NB-IoT network. So these equipments are responsible for transmitting and receiving the data. Then we have the NAC. NAC is network access controller. So it will control the access between user equipment and evolved node B. So the access is being controlled here. Then we have RRC. RRC is radio resource control. So radio resource control is a protocol layer which is responsible for controlling radio communication between the UE and the network. So this will establish, maintain and release the radio connection. Then we have PDCP. PDCP is packet data convergence protocol. It will handle data compression and encryption at higher layers. Then we have RLC. RLC is radio link control. So this will ensure that reliable data transfer is happening between the UE and ENB. Next, we have medium access control. Medium access control will control the access to physical channel. It will determine when and how each device will communicate over the shared interface. Then we have PHY, physical layer. So actual physical transmission happens here. Then we have MME. We have MME. Then we have MME here. So MME will manage mobility and session setup for devices. MME stands for Mobility Management Entity. Then yeah, we have covered mostly all of the parts. Then we have ENB. ENB is the evolved node B. So this is like a base station in LTE network which is responsible for taking care of communication. But all the important points here, and we have covered all this. Speaking of the deployment and use cases of NB-IoT, first one we have is the smart meters. Smart meters are used for electricity, water, gas. Environmental monitoring, it is to monitor the air quality, temperature sensors and so on. Agriculture IoT for soil moisture detection and other things. Smart cities, waste management, street lights and all of that. Deployments, we can say that NB-IoT can be deployed in urban environments, rural areas and indoor locations or underground within buildings because it has robust coverage. Speaking of advantages, first one is battery life. Battery life can be up to 10 years, we have discussed, right? Then low power consumption. So it has great battery life, so less power will be consumed. Then coexistence with existing cellular networks. This is one of the major advantages because of which we need not spend more money on the infrastructure. Whatever is there, existing infrastructure is there, make use of it. Then security. So we have strong security features which will ensure confidentiality, integrity, and authentication is maintained in terms of security. Speaking of the limitations, let me write it down here. First one is high device complexity. High device complexity means compared to the long range or Sigfox, these devices, no, they are generally more complex and they are expensive also. Then we have low data rates. So this is not suitable for applications that will require high speed data transmission or real time communication. And the major advantage is no mobility support. So because these are only designed for static applications. So this was all about NB-IoT. Moving on further, we have Wi-Fi. So Wi-Fi is pretty popular. We can write Wi-Fi as IEEE 802.11 also. So Wi-Fi is widely used wireless networking technology that enables local area networking for devices. So it operates under IEEE 802.11 standards, offers a defined range within homes, offices, and public spaces. So look, speaking of the frequency bands, it operates in 2.4 gigahertz to 5 gigahertz ISM, industrial, scientific, and medical bands. So these bands are divided into multiple channels which enable multiple devices to share the same frequency spectrum, and there is no issue of interference. So Wi-Fi uses carrier sense multiple access with collision avoidance to manage the channel access. Speaking of the multiplexing, so we have TDMA, that is time division multiple access, which allows multiple devices to share the same channel by assigning each device specific time slots for communication. Speaking of versions, so different versions of IEEE 802.11 standard will have different capabilities. So the first one is 802.11a, which operates at 5 gigahertz and it provides up to 54 Mbps using OFDM. OFDM is orthogonal frequency division multiplexing. Then we have 802.11b. So this operates at 2.4 gigahertz and supports 11 Mbps or 10 Mbps data transfer. Then we have 802.11g. So it also operates at 2.4 gigahertz but achieves 54 Mbps using OFDM, similar as the above one. Then we have 802.11n. It works both on 2.4 gigahertz and 5 gigahertz bands, offering speed up to 140 Mbps using advanced MIMO techniques, multiple input, multiple output techniques. Speaking of the data transfer and range, Wi-Fi supports high data rates suitable for multimedia and internet-based applications. The range depends on factors like frequency band and obstacles. So 2.4 gigahertz is it offers a long range, but speed is less here. Whereas 5 gigahertz will provide high speed but shorter range. Then we have this figure, which is of IEEE 802.11 Wi-Fi stack. So the first layer which we have is physical layer. Physical layer will handle actual transmission of data. This will happen through radio waves here. Speaking of data link layer will provide the medium access control protocol and other things, data transmission, checking the data if there's any error or not, correcting the errors and all of that. Speaking of network layer will support routing and IP addressing. Then we speaking of transport layer, it will ensure reliable data transfer is happening, all the protocols, TCP, UDP and all. Then speaking of session presentation application, they handle the user facing aspects like file sharing, video streaming, web browsing, all the communication aspects from user side, all those would be handled here. Next, the next figure we have is Wi-Fi deployment architecture. So let's see, first one we have is access points, APS. So these are hardware devices like wireless routers that provide wireless access to the devices within this particular range. Then we have Wi-Fi routers here. Wi-Fi routers are, they connect the wireless network to broader internet. The connection is happening, right? So, and they'll ensure that data transfer is happening through internet. Then we have the hosts. Hosts are the devices here. So it could be laptop, smartphone, any IoT device, right, which can share the data. Then speaking of the applications, first one we have is home networking. Home networking is in we can make use of laptops, TV, and other IoT devices in our home itself. Then business networks. So because Wi-Fi offers seamless connectivity, we can connect many systems in our business office, right? Then we have public Wi-Fi. So this could be in the airports, libraries for free internet access and all. Then IoT integration. So connecting cameras, lights to a central network which can access the signals or access the information through Wi-Fi and then perform the operations accordingly. Let's take street lights. Street lights are one of the examples under the public or smart cities where we need not connect the cameras through wired connection to the server or wherever they handle all these things, right? It is all transferred through Wi-Fi. Speaking of the advantages, first one we have is high speed. That is high data rate is there here, so it is used for video calls, gaming, and all of that. Then we have flexibility. That is, it offers wireless connectivity. It reduces the need for excessive cabling. Then we have compatibility. Many devices are compatible to Wi-Fi. Scalability, it supports multiple devices within a single network. Speaking of limitations, first one we have is the range. So it has limited coverage if we compare it to Sigfox and long range. Then you have interference. It is susceptible to any interference if it is of same frequency band. Then power consumption. So it consumes more power compared to the other technologies. And security. It requires a proper strong algorithm or encryption algorithm to protect. Unless, if not, it is very easy to break or access the data here. So this was about Wi-Fi. Next we have is Bluetooth. So Bluetooth is defined as, let me write it down here, IEEE 802.15.1 standard is called as Bluetooth. So defined by IEEE 802.15.1 standard is short range wireless communication technology designed for low power consumption between two or more devices. Initially, it developed as a cable replacement technology. It supports both data and voice transmission. Speaking of the key features, first one we have is the frequency band. It operates in 2.4 gigahertz ISM band, and it offers frequency hopping spectrum, spread spectrum FHSS to minimize any interference. Then we have adaptive frequency hopping AFH, which performs 800 hops per second across 79 channels, each 1 megahertz wide. Then speaking of the range, it is typically range is approximately 10 meters, although it can vary depending on the environment factors. Then we have the basic rate mode. So in basic rate mode, we can transfer the data using Gaussian frequency shift keying modulation. It supports data rates up to 1 Mbps. Then speaking of the advanced modulation schemes, which involves 4 DQPST, which is of 2 Mbps, and 8 DQPST, which is of 3 Mbps per second. Then then let's look into this figure. Bluetooth device network architecture. Here we have two main things. Piconet. So Piconet is a small localized network with one master, and up to there could be 7 slaves here. So a slave can be part of one Piconet at a time. Then we have scattered net here. Scattered net is formed by interconnecting two or more Piconets. So it is like a bridge device which will connect two Piconets, serving as slave in one and master in the other one. So this was about the figure, mainly speaking of Piconet and scatternet. So that's how the architecture is there. So data transfer from one device to another device happens. Always the master and slave signaling is established here. Then speaking of the applications, so the first one we have is personal area network, smartphones, laptops, headphones, and all. IoT integration, smart home devices, wearable technologies like smartwatch and so on, medical sensors and other things. Data transfer is we can share the data, file sharing, device synchronization, all that could be done through Bluetooth. Audio and telephony. So powerful wireless audio devices and hands-free communication can be done through Bluetooth. Speaking of advantages, low power consumption, making it ideal for battery powered devices. Then we have interference resistance. That is, we make use of FHSS and AFH, which will minimize if there are any crowding happening. Then we have cost effectiveness. It is widely available and inexpensive to implement. Speaking of security, we have encrypted communication and service level security, which enhances the protection. Speaking of limitations of Bluetooth, again, short range is one of the problems because it is only limited to 10 meters. Then we have low data rates compared to Wi-Fi. Data rate is less here. Scalability is Piconets can only connect a limited number of devices, that is 7, right? Not more than that. Then we have interference in crowded environment because if similar frequency is available, then there could be interference happening here, which can again lead to data loss and all. So this was all about the Bluetooth. Next we have this figure, Bluetooth protocol stack. So let's look into this protocol now. The stack now. First one we have is physical layer, physical radio. So it handles transmission of radio signals. Then we have baseband layer, which manages the physical link between the devices. Then we have logical link control and adaptation protocol, L2CAP. It is responsible for data segmentation, flow control, data integrity, and all of that. Then we have LMP, link manager protocol. So link manager protocol will perform the setting up of connections, data transfer, and all of that. Then we have host controller interface. Host controller interface will provide access to the hardware controller and facilitate device discovery. Then we have RFCOM, radio frequency communication, which acts as a cable replacement protocol, ensuring that there is serial data streaming or data transfer happening. Then we have service discovery protocol, SDP, which discovers service by providing other services. Then we have application layer, which supports user facing functionalities like audio or telephone services. So this was all about the Bluetooth protocol stack. So we have reached to an end in this particular module. We have covered all 15, 16 IoT connectivity technologies. So if you have not watched those videos, I would suggest you to go through the playlist and cover those videos. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.